Roughly 3 years ago, I was in Germany then, and I was waiting in a bus stand to get a bus to my university. And in the bus stand, I was waiting, and I found that there are two charged balls connected with a string carrying charge Q and Q. Now while I was waiting for my bus to come, I was thinking that if this string is suddenly cut with a scissor, then at what acceleration will these two charges start to move away from each other? Because I knew that these two charges are repelling each other because of their like charges, and the string is holding them together against the Coulombic repulsion force between them. So therefore, if the string is not there, they will repel each other and they will attain some velocity in the opposite direction. And how much will be the acceleration immediately after the string is cut? Now, while waiting for this bus, I calculated that the force between them, repulsion force, is F is equal to QQ divided by 4 pi epsilon r squared, where r is the distance between them. And I knew that the mass of both the particles, both the balls, were m and m, same. Therefore, the acceleration A would have been given by the force divided by the mass. And if I call this force as q square by q square times some constant k, where k is equal to 1 by 4 pi epsilon r square. Everything is known to me. Epsilon naught, the permittivity of free space, 4 pi, the value of the distance, everything is known to me. So therefore I know this value k. So therefore the acceleration would be kq square by m. This is what I calculated. But then the bus came and I went into the bus, and the bus started to move, taking me towards my university. And while traveling in the bus, I thought, was my calculation correct? Let's check my calculation once again. What will be the acceleration if the string is cut suddenly? So now, then I'm in the bus. I'm inside the bus, and the bus is taking me towards my university at a velocity or speed of v. And this bus was moving very uniformly without any jerk or any hassle. You know, it was Germany, so roads are very nice and flat. So buses there really move at uniform velocity. Yeah, it's possible there. You might also be thinking that how could one find two charged balls in a bus stand? Yeah, you remember this is Germany, the country of Einstein. So this is not really abnormal, this is not unexpected, I mean impossible to find two charged balls in a bus station in the country of Einstein. Okay, so now inside the bus, I recheck my calculation. And when I started, I immediately realized that these two charged balls are no longer stationary with respect to me. They are moving, and they are moving with the same velocity v in the opposite direction away from me. So my calculation that I did previously need not hold good anymore, because previously I did not consider the Lorentz force that may appear between these two particles when they start to move and they create a magnetic field. So I thought let's recalculate considering this velocity once again. So now these two charged particles are moving with a velocity v with respect to me. You know that actually I am moving on the road and these particles are stationary in the bus stand, but they are moving with respect to me with a velocity v. And when these particles are moving with a velocity v, you can consider them as small electric current, localized electric currents at this point and at this point. Therefore, they will create their magnetic field surrounding them. And therefore, if you consider, for example, this particle which is moving from right to left, and it will create a magnetic field which will be like this, dots here on this side and cross on the other side. Okay, so magnetic field, magnetic flux lines come out from the paper, goes round this ball and enters the paper once again here. So here I have dot flux, that means flux coming out from the plane, and this ball is moving with a velocity v. So therefore there will be some Lorentz force acting on this ball. And how much that force will be? That force, you know the formula, it depends on the charge and the cross product between the velocity and the flux density. Now I can calculate these flux densities created by this charged particle, because I know the value of charge and I also know the velocity. So this value I can calculate. And then I observe the direction of this force will be on this particle will be like this, okay, upwards, because v is in this direction and b is upwards. So you take the cross product and you will get this is the direction of the force. So that means this force will pull this charged particle towards the other charged particle. It's like an attraction. Okay, so as if this force is pulling this charged particle towards the other charged particle, or this charged particle is being attracted towards the other charged particle. In the same manner, you can calculate the magnetic field generated by this charged particle here, and therefore the force acting on this other particle. So if I do that for this charged particle, the magnetic field created will have cross sign here on this side, and therefore this charged particle will experience a force downwards. Once again, you see this is a force of attraction. Verify yourself, don't trust me. Verify yourself. I claim that this is a force of attraction. And now how much this force will be? For that I need to find out the value of B. That I can do. And when I did that, I found that this B depends on the velocity of the charged particles. Why? Because faster the velocity is, the equivalent current that you consider is also large. If this charge is moving faster, you can think that there is a localized current which is also large because it's now moving faster. And therefore, the magnetic field created will also be larger. So this B depends on V. And I found that this force, its magnitude is therefore equal to QV, this thing, and the magnitude of B, which is also proportional to velocity and also proportional to the charge. Because more the charge, the equivalent current is larger, and therefore magnetic field is larger, and therefore the force of attraction is also larger. So it came out that this is proportional to Q square V square according to my calculation, and I put the proportionality constant Q square, which I can calculate, which I did calculate, and this was the force of attraction. Now, how much is the net force between these two particles or the balls? This is equal to F repulsion minus F attraction, minus because they are in opposite direction, and I am only talking about the magnitude right now, and it came out to be this repulsion force kq square by m. Okay, I call this as k1 q square, where k1 is k by m, another constant. So this became k1 q squared minus k2 q square v square, and therefore it became k1 minus k2 v square q square. So this is the sorry, a small mistake. F is equal to k, so this is k, this is k, this is k. I don't need this. I hope you recognize that. F is equal to k q square, which I put here, and I get this k minus k2 v square times q square. And so therefore the acceleration A would be k minus k2 v square by m times q square. So this is what I find when I did this calculation inside the bus, and this is what I find when I did the calculation standing in the on the platform, on the bus stand, or you can call that platform, outside bus. So E here and E here, A for acceleration, they are different. And they are definitely different. Here kq square by m, here kq square by m minus k2 v square q square by m. So this is smaller compared to this. How is that possible? How is that possible? I think the acceleration of these particles should be same no matter how I calculate, no matter whether I am inside the bus or outside the bus. How is that possible? Because you know, I can argue in this way that if these are the two particles with their positions, or any particle with the position along the y-axis of this particle is y, and this is what I see or measure when I am on the platform. And then while I am in the bus and the bus is moving, I shall still measure this distance as y, even from the bus, right? So, and if this y is a function of time, because maybe this particle is moving, because they will move when I cut this string between them, they will accelerate and they will move, so this y will become a function of time, but this y will be same as measured from the platform and as measured from the bus. And therefore, if I call that yp is the measured distance y from while I am standing in the on the platform, this is equal to y as measured from the bus t. Now if I differentiate this, I get dyp t dt is equal to dyb t dt. If I differentiate it once again, dyp d2yp dt2, and this should be equal to second derivative of, and this is nothing but the acceleration as measured from the platform, and this is nothing but the acceleration as measured from the bus. These should be equal, but according to my previous calculations, which I did once when I was standing in the on the platform, I found the acceleration ap was this much, and when I was in bus, inside the bus, I calculated the acceleration to be different. How is that possible anyway? Same particle moving with two different accelerations as measured from two different frames. Am I doing any mistake? Is there any mistake in my calculation? Or is it that what I have learned so far all about physics, everything is wrong? I leave it to you.